classify some geometric isomers as cis-trans isomers. All right, so cis and trans are spatial relationships between substituents on a rigid structure, where for cis, the substituents are on the same side, and for trans, the substituents are on opposite sides, okay? Now, here's the catch. We use cis and trans when we're talking about, we can use cis and trans when we're talking about double bonds and when we're talking about rings. But it's very specific, okay? So we can only use cis and trans when there are exactly two substituents on the double bond or the ring. So let's look at the ring as our first example, okay? So this molecule up here, we have a ring and we have two substituents. We happen to have two methyl groups, okay? Now both of them are on wedge, which means both of those substituents are coming out of, in front of the plane of the page. In other words, they're both going up, if you will, okay? Because they're both going the same direction, we would categorize this molecule as cis, because the relationship we have between these two substituents is that they're going the same direction, okay? If we look at this one on the end, we have, again, two methyl groups, but now both of them are on a dash, okay? But that doesn't matter. What matters is the relationship. So this is down, if you will, and we're going to call this down. Since they're both going behind the plane of the page, since they're both going the same direction, this relationship is cis, and so that molecule is cis. Okay, the one in the middle, we have one methyl group going on a wedge and one methyl group on a dash. Because they're going opposite directions, the relationship is trans. Okay, now let me erase some of this. So it's very easy to figure out cis and trans on a ring when you have two substituents. If we had more than two substituents or less than two substituents, we wouldn't be able to describe them as cis or trans. It wouldn't make sense. So for example, if I draw in another methyl group here, okay, the question is, okay, now what is this compound? Is it cis or trans? Well, the question doesn't really make sense because the two substituents here are related by going opposite ways. So the relationship between these two is trans, right? But then the relationship between, oh, those are similar colors. The relationship between this methyl group and this methyl group, well, they're both on the same side, so that would be cis, right? So it doesn't make sense because when you have more than two substituents, you have more than one relationship, okay? So you can only do cis-trans on a ring when there's exactly two substituents, okay? Now there is a catch. There is, I guess, one more little thing that you should know. For example, let's draw a ring up here. We'll make it a six-membered ring. All right, and I'm going to put two substituents on this ring. So I'll draw one here. And I'll make this a bromine. Now, if this bromine is on a wedge, and I wanted to put another substituent on this carbon where the bromine is, it would have to be on the dash because that's the only bond left. So let me just say this is a chlorine, let's just say, okay? So here on this ring, I do have two substituents. I have the bromine and I have the chlorine, but they are both bonded to the same carbon. So even though I have two substituents on this ring, I would not give a relationship of cis-trans here because it doesn't really make sense if the bromine is on a wedge, then because of the geometry of this carbon, that means the chlorine has to be on the dash, always, okay? If I drew another 6-membered ring and I put the chlorine on the wedge, what would the bromine be on? Well, the bromine would have to be on the dash because that's the only bond that's left for this carbon, okay? So when you have two substituents and they're bonded to the same carbon in a ring, you don't use cis or trans for relationship because the relationship is already given by the fact that this carbon has to have one bond going in the wedge and one going in the dash direction, okay? So let's look at double bonds. Double bonds, there's a lot of similarities between double bonds and rings when it comes to cis-trans. So here, again, you only want two substituents, okay? And you want them to be on different carbons. So here I have this methyl group and this methyl group. You can see that they are pointed, if you will, in opposite directions. If they're in opposite directions, they're going to be a trans relationship, okay? Whereas this molecule here, they are both going in the same direction, so the relationship is cis. Now, if I had a double bond and both of my substituents were on the same carbon, for example, a bromine and a chlorine again, right? I could not use this relationship, cis-trans, to describe the bromine and the chlorine because, again, when they're bonded to the same carbon, one of them needs to be going in the upward direction, if you will, and if the chlorine is bonded to the same carbon, it has to be going in the other direction based on the geometry of this carbon. We know that this carbon has 120 degrees between each of its bonds, and so that dictates where this bromine is and where this chlorine is. So just like with the rings, if your two substituents are bonded to the same carbon, you don't use cis and trans to describe that relationship. The other problem, with cis and trans, with the ring, is we couldn't do it when we had more or less than two carbons. We could only do it when we had two carbons. The same thing applies for double bonds. When you have more than two substituents on a double bond, you can't do E and Z. Or you can't do cis and trans. You have to use a different way to describe the isomerism, and we're going to use E and Z nomenclature to distinguish the geometry of a double bond when a double bond has more than two substituents. So here, for this molecule, we could call this molecule cis, okay? But this molecule, it doesn't really make sense because this and this have a cis relationship, right? But this and this have a trans relationship, okay? So it really doesn't make sense. Okay, so we can't use cis and trans for this. So what do we use? Well, again, that's where we get into E and D.